in the Center for Water Resources Research. Today, I have the pleasure of giving you an introduction and overview of the Google Earth Engine platform. So I just want to preface today's talk by saying that treat this as an informal session. Feel free to interrupt me whenever you feel the need to. If you have a question, if I'm going too fast, you'd like me to slow down. If there's something you're unclear about, just raise your hand or unmute yourself and ask me in case I don't see your hand up or any question in the chat. Okay, so I have a short presentation just to give an overview of Earth Engine and explain why we want to use this specific platform, and also just to revisit some of the concepts in relation to remote sensing and satellite Earth observation. I believe my colleague, Ms. Chetty, gave you quite a comprehensive overview yesterday, so some of these things might be familiar, but if you're unclear about anything, we will be discussing them again today. So I'm just going to share my screen quickly. Okay, so please let me know if you can see my screen.
Yes, we can see your screen.
Yes, we can.
Yes, we can see the screen.
Okay, perfect. Skipping on its own. Okay, so as I said, today's talk or lecture is going to be about looking at the use of Google Earth Engine, but more broadly speaking, we're looking at the estimation and measurement of hydrological variables using remote sensing, and more specifically satellite Earth observation data. So there's different types of remote sensing platforms that one can particularly use, but in this specific instance, we're looking at satellite Earth observation data. Conventional or traditional approaches used for the estimation of gravity. Sorry about that. I think there's an audio playing over here. Okay, yeah, so why do we want to use remote sensing? So our conventional measurement approaches have been extensively applied and proved invaluable in furthering our understanding of the role which hydrological processes interact and how they interact with each other within the environment. And yeah, from having these in situ based approaches, we've got quite a good in-depth understanding about the importance of these different variables, the factors which influence them, how changes over time to land use, to land cover, to different management practices, and so on will affect these different processes. The challenge, however, with these in situ based approaches is that their application is limited by their spatial representativity, the costs associated with these approaches, as well as the labor requirements. So they're quite intensive. They require a lot from us, from a financial perspective, but also from a time perspective. And they are limited in what information they can provide us. So they can provide us with a lot of very in-depth information, but they generally only representative at small spatial scales. Remote sensing data, which, as I mentioned, they could be multiple platforms. So you get satellite Earth observation approaches, you could get manned aerial vehicles or unmanned aerial vehicles, which have sensors attached to them. These are alternate data acquisition approaches, and they present a suitable alternative for us to acquire hydrological process information. Sorry, I seem to have stopped sharing my screen. Just get it back quickly. Is it still not in screen sharing mode? Is it conventional or traditional approaches used? Is it back up? Before delving. Seem to be having some technical difficulties, sorry. Okay, so yeah, so we ended off with this slide here where we are looking at why would we want to use remote sensing? So as I said, it presents a suitable alternative for us to acquire hydrological process information, and it helps us overcome many of the limitations that are associated with these traditional approaches. So remote sensing techniques have a wide range of applications in environmental studies. And to define what it is, it's the process of detecting and monitoring the physical characteristics of an area by measuring reflected or emitted radiation. So you have sensors attached to these different platforms, which can capture reflected or emitted radiation from several parts of the electromagnetic spectrum. So on the slide here, the figure at the top is just giving you an indication of how electromagnetic energy is distributed within this electromagnetic spectrum. And there's a portion here that we've highlighted, which is in relation to the visible light. So this electromagnetic radiation that's distributed along the spectrum will have data captured or represented at different wavelengths. So we can measure the properties of this radiation at different wavelengths. You get sensors that can be classified as active or passive. An active sensor is a sensor that emits its own radiation and then measures that radiation that it has emitted when it is reflected off the Earth's surface and returns back to the sensor. Or you get passive sensors which rely on the energy emitted by the sun. So the sun will emit some radiation that is reflected off the Earth's surface of clouds, and then that sensor measures the radiation that's returned or reflected to it. So different objects will return different amounts of energy in different bands of the electromagnetic spectrum. So when we're making reference to these bands, we're just talking about the electromagnetic radiation at a specific wavelength. Okay, so is everybody still with me?
Yes.
Okay.
Yes.
All right, so now that we have sort of a broad understanding of what is remote sensing, why we want to use it, some of the properties associated with the data. So we've spoken about different wavelengths where information is captured, but there's also other properties associated with these data sets. So generally we think of three main properties. So we get the spatial resolution, the spectral resolution, and the temporal resolution. So one of the most common things that we focus on is the spatial resolution. So we either define it as coarse spatial resolution imagery or moderate to high spatial resolution imagery. And these types of imagery have their own unique characteristics, which make them fit for specific purposes. So just using an example of evapotranspiration. So we wanted to use coarse spatial resolution imagery to estimate evapotranspiration. What are the advantages and disadvantages associated with this type of imagery? So firstly, coarse spatial imagery has quite a high temporal resolution. So if we think of a sensor such as MODIS, MODIS can capture data for us on a daily time step. So we can get nice temporal trends and seasonal understanding of how ET is changing within a year and between years. But the limitation that's associated with a sensor such as MODIS is that it's quite coarse. So what tends to happen is that the pixel size of the image generally exceeds the area under observation. So you aren't accounting for the heterogeneity within a specific area. So if you had to look at the figures here, which are basically describing what I'm saying, at the bottom here, we have some information contained within a pixel. So over here, it's showing that there's a house and there's some land surrounding this house. So at a 30-meter pixel resolution, if you look at the top and you look at the bottom, this is what we'd see. So at the bottom here, it's saying that at this 30-meter pixel resolution, it's assigning the dominant information of the dominant land cover to the entire pixel. So it can only represent the house within the spatial resolution. As we move down to the finer spatial resolution, where we're looking at the 1 meter pixel, we can see that we're now able to more adequately capture the heterogeneity within this region of interest. So each individual feature of the house can be captured, and each individual feature of the surrounding landscape can be captured. So that's the trade-off that we tend to have with the imagery that we most frequently use. So I should have preface this by saying that more often than not, this is in relation to freely available imagery. You can pay quite considerable amounts for high resolution imagery that's available more frequently, but for the purposes of this talk and majority of the research that we do, it's the freely available imagery that we're interested in. So moving away from the coarse spatial resolution, we have either moderate or high spatial resolution imagery, depending on what we want to apply that particular image for something like the estimation of evapotranspiration. The moderate to high spatial resolution imagery more adequately captures the spatial heterogeneity within an area. But the trade-off with that is that that image is available less frequently than the coarse resolution imagery. So it makes it a bit difficult for us to pick up seasonal trends or the influence of a specific weather event on that variable of interest. Everyone still with me? Need me to explain that again?
We're still here.
Yes, please.
Okay, so which part is a little unclear that you'd like me to run through again?
Just towards the end there, I had a sort of a power cutting for a few seconds there, so I couldn't hear you well.
Okay, so no problem. So while I'm explaining this again, just look at these images and try and relate what I'm saying to the specific image, right? So when we're talking about coarse spatial resolution imagery, the features that are associated with this, or one of the advantages, is that the coarse spatial resolution imagery is generally available a lot more frequently than your finer resolution imagery. So if we want to do routine monitoring and detect changes over time, this type of characteristic is an advantage for us. So the coarse resolution imagery is good to monitor seasonal trends, interannual trends, the impacts of specific events on our variable of interest, whereas the moderate to high spatial resolution imagery is available less frequently. So we can't do the same things with it. But the advantage of the moderate to high spatial resolution imagery is that for a particular area of interest, we're able to capture a lot more detail in terms of spatial heterogeneity. So if you had to look at this diagram at the bottom showing low spatial resolution all the way to high spatial resolution. In the low spatial resolution, we have this very large pixel. And within this large pixel, there's only a certain level of detail that we can represent. So generally, the dominant feature that's present in this pixel, the entire pixel will get assigned that information. So if we look at this example with the house and the surrounding landscape, at this very coarse resolution, we can't represent both the house and the landscape. So since the house is the dominant feature, it gets represented as that entire pixel contains the house. So that's the trade-off that we get. So a lot of the time, like with your coarse spatial resolution imagery, it will exceed the size of the area under observation. So if you're thinking of a smallholder farm setting, which is quite diverse, and they've got different crops and different land use, land cover practices within that area, if you had to use a very coarse resolution image, you won't be able to detect any of that spatial heterogeneity. What it might demonstrate within that pixel is that that entire smallholder farm setting is agriculture, when we know that's not the case. Or even if it is agriculture, it's not one specific type of agriculture. So that's the sort of trade-off we get there between the coarse resolution and the moderate to high resolution. And then there's also the temporal resolution that's attached to it. So as I said, the coarse resolution imagery tends to be available a lot more frequently. The finer resolution imagery, not as frequently. So it'll have a longer revisit time, which can still be impacted by things such as clouds and so on. And the third characteristic that is important to be aware of is spectral resolution. So this is the amount of detail that is captured in terms of capturing information in a specific band. So if we go back to this previous slide here and you see this diagram of the electromagnetic spectrum, you'll see that there's information that can be captured within different portions of the spectrum. So you get visible information, you get near infrared, you get thermal infrared, and so on. So the spectral resolutions in relation to how much of detail is captured within the electromagnetic spectrum. So for instance, a sensor such as MODIS will probably capture information in 36 bands, whereas something such as Landsat will capture information in 16 bands. This becomes quite important if we're thinking of an example of mapping land use land cover. So when we want to map land use land cover, we want to try and get as many unique features associated with the specific land use land cover class as possible to help us differentiate between that class and another class. So when we have a very high spectral resolution, we're able to more easily do that as opposed to having a coarse spectral resolution. So we're not able to capture as much detail about that specific feature of interest, which makes it a bit harder for us when we do our modeling at a later stage to sort of predict what land use land cover is present within that area. Everyone still with me?
Yes.
Okay, good. Okay, so moving on, so we've discussed why we're interested in remote sensing, some of or what remote sensing is, some of the characteristics associated with the data. And now we're going to start moving on more towards how we actually work with this data and analyze it. So the advantages of using remote sensing data for the estimation of hydrological variables has been well documented. And advancements in data capturing using remote sensing technologies coupled with higher computing power have facilitated the quantification of spatially explicit estimates of variables across space and time. And it's allowed us to acquire invaluable information for the monitoring and preservation of the environment and different hydrological and agricultural systems. Despite all of these advantages, there are a lot of disadvantages which may create barriers to many people who are actually interested in using this data. So firstly, let's think of some of the computational limitations. So there's large volumes of remote sensing data, mainly satellite Earth observation data that have now become widely available for analysis. So for example, the Landsat 7 project, which commenced in 1999, captures about 300 images per day. This is equivalent to more than 1 petabyte or 1 million gigabytes worth of data. And then despite this data being freely available and accessible to most people, handling and manipulating these large data sets often proves to be a major challenge. So if you think about just Landsat 7, if you are interested in performing an analysis from 1999 until present at the continental scale, the volume of data that you have to firstly download, to store, to process, to store the newly processed information, it becomes quite computationally intensive. And more often than not, we tend not to have the computational resources available to us or the skills to work with these large volumes of data. So that becomes a major stumbling block for us. So considering that there's so many advantages associated with the use of remote sensing data, and there are these disadvantages which may prevent people from exploiting the capabilities of remote sensing data. In the past 5 years or so, Google has developed a platform that is capable of storing and analyzing these large volumes of mainly raster data, but it's housed on their computing infrastructure. So majority of what you will be, or what we'll be discussing and demonstrating shortly is, this is a cloud-based infrastructure. So while you are connecting to it via your PC, the actual analyses that are being performed are done using Google's computing infrastructure. So Google Earth Engine is defined as a geospatial data analysis platform, and it has been specifically designed for the provision of access to this extremely large and diverse catalog of satellite Earth observation data, which has now become available to us. It has built-in algorithms which assist you with performing many of the processing tasks that you would commonly utilize. And it also has a programming interface for you to run these built-in algorithms or create customized algorithms for your specific needs. So this image here at the bottom is just giving you an example of some of the commonly utilized data sets that are available over there. So the Landsat and Sentinel entire image collection is available on the platform. MODIS is the entire collection is available on the platform. There's terrain elevation data, there's land cover data, there's atmospheric information. And the advantage is it's a one-stop shop for everything. So rather than you having to access multiple different websites and platforms to download data, you now can access everything from a central repository, perform your analyses, and then export only the data that you are interested in. So it's an extremely powerful tool. And hopefully after today's talk, you'll see the benefits of using it and actually implement it in your own research. So before I go into the live demo of Google Earth Engine, anything anyone would like me to explain again? Okay, so let me get into the fun stuff. That's not what I want to share. Okay, so can everyone see my screen now?
Yes.
Yes.
Okay, so if you, well, I'm assuming you are connected to the internet. So if everyone can just go quickly onto your Google search engine and type in Google Earth Engine. So once you type in Google Earth Engine, let me just go back. This should be your first search result at the top. It says Google Earth Engine. Just click on that and it will bring you to the home page. Okay, so before we actually go into Earth Engine itself, I'm just going to play this video, which will hopefully much better summarize what I've just been discussing regarding the capabilities of Earth Engine. So yeah, quite a nice informative video, gives a good overview of what Google Earth Engine is capable of. Now into the actual fun stuff, actually working with Earth Engine. So if everybody can go to this tab right at the end where it says sign up, you just click on that. So this is a bit different for me because I've already signed in and I have an account, so it might look different on your end, but please provide all your information and create an account on Earth Engine. It takes about 2 days for the processing to be done, but it's freely available, so there's no concerns about you having to pay for anything or agree to any specific conditions. It's freely available for research purposes. So once you've created an account, you can then go back into the main page. Under platform, you see it provides us with the overview, the code editor, explorer, documentation. So when you actually want to work with Earth Engine itself, we go directly into the code editor. So this is the programming environment that's made available to you to perform all of your analyses. Okay, so can everyone see the code editor?
Sorry, what did you say?
I said, can everyone still see the code editor? My screen is still showing. So this environment here that we're sitting in, where you can see there's like a map and this blank white space, this is the code editor environment. So this is actually the Google Earth Engine environment. Can everyone see that?
Excuse me?
So on my
Yes.
screen, okay, cool.
Excuse me? Okay, some people are having problems because they're using the same laptop to listen to your presentation and the same laptop to do the practical. So it's becoming difficult for them to see what you're doing and then to actually practice what you, on the same laptop.
Okay, so no problem. So as long as you know where to sign up, then for now, just focus on my screen. Don't actually try going into Google Earth Engine. So I'm just going to go back quickly just to show everyone again. So once you're on the home page, you click here to sign up, you fill in all your personal details, and then within a day or two, you should get a confirmation via email that your account has been set up. And then you can actually access the Google Earth Engine platform. So you can do that in your own free time. You don't have to necessarily try and follow along now because you won't be able to. So just be aware of where to sign up. And then once you've signed up and you want to return into Google Earth Engine to revisit some of the things that we discussed today, you click the platform tab and you go to code editor. And then it opens up the code editor page. So is everyone now following on my screen? Can you see the code editor page?
Yes.
Yes, we can see.
Okay, perfect. So,
Yes, but sorry, I'm there, but I'm using another gadget, but there's a message to say, welcome to Google Earth, then select an existing cloud project. Should I say back or select?
select an existing ground project. I'm not sure why it would come up with that. Just go back.
Okay.
Okay. All right, so back into Google Earth Engine. So this is what the platform actually looks like. It doesn't look like anything very appealing. You see, we've got 4 different widgets or screens over here. We've got some information here on the left. We've got this blank environment in the center. Another screen here, which is showing us multiple tabs, and then we have a map at the bottom. So this is the code editor environment where you do basically 90 95% to 100% of your analysis, depending on how you want to work with the data and extract it. I'm just going to run you quickly through the different functions that are available here within the code editor environment. So under this tab here, scripts, this is all the different types of code that you would have either written for yourself and saved, or all of the demo examples that you can access. So at the top here under scripts, it's got owner. So these are my personal scripts. So things that I have, other projects that I have completed where I've written the code for it and saved it. I can create my own repository and save all of the information in here. Earth Engine, once you sign up, as long as you've got a Google account, I think it gives you 10 gigabytes worth of storage data. So all of these scripts will be stored within that 10 gigabytes that's allocated to you. And you also have the ability to upload some of your own vector data or raster data if you have any that aren't accessible via Earth Engine, but you still want to use the platform to do your processing. You're more than welcome to upload it, but it all forms part of that 10 gigabyte allocation that's made available. So let's just ignore the owner scripts. So if you come down, there's this reader tab. This is basically if other people have designed specific workflows or codes for you to perform a specific analysis, you can upload their code into your environment. So you don't have to keep on copying and pasting. You can just call up their information and then run their code. And then there's examples, so demo examples of how to work with Google Earth Engine. So we'll go through some of these shortly and just giving you a quick tour of the platform. Then we have this docs tab, and this is all the built-in functions available within Earth Engine. So if you want to get more clarity on what a specific task is doing, what data or what inputs are required for you to execute that task, you can come here in this docs tab. You can search for it by name. So if you want to filter the method, let's just type in something and see what comes up. You can search for it by name, or you can just navigate through this list here. Let's go on the algorithms quickly, and Sentinel-2, click on it. So it explains what the specific function is doing, and then it tells you the arguments of the different types of inputs that are required to run this function. As I just mentioned, you can upload your own data onto the platform. So if you don't want to work with what's available on the repository, or something you need to work with is not available on the repository, you have the ability to upload your own data. So a lot of the time there'll be shapefile boundaries for a specific area of interest that is not available, and then we want to limit our analysis to that spatial domain, so we'll upload that shapefile in. Or you could, if you have your own raster data, for instance, some of the work that I'm doing now involves the use of drone imagery. So I can upload the drone imagery onto this platform and then make use of all the available functions and the computing power of that to speed up the processing that I'm doing or that I require with Earth Engine. So I can take advantage of all the capabilities of Earth Engine, even though the data that I want to do the analysis on is not available within the platform. So that's another nice feature about Earth Engine. Yeah, so if you want to upload your own data, you come to this assets tab, and you click the drop down new, and then you see it gives you different options of the type of data that you can upload. So you can upload, excuse me, a geotiff image. You could upload a shapefile, you could upload information captured within the CSV. If you're working with multiple satellite images from a specific sensor, let's say Landsat, you've got 10 different Landsat images sitting in one folder, you could upload the entire image collection rather than doing it individually, or you could just upload the entire folder. Okay, so this specific viewing window, does everybody have a basic understanding of what the scripts, docs, and assets tabs provide you with? Okay, I'm going to take the silence as everything is good. So this main window here in the center, this is where we actually write our code and we perform the different functions. So when I open up one of the codes that I've written previously, you'll see exactly how it's compiled and documented within this viewing window. And once the code is in here, there's different things that we can do with it. So let me just call up one quickly without actually running it. Okay, so this is a code that I've developed and compiled to do land use land cover mapping based on my knowledge of a study area and trying to do the mapping on the image captured by a drone. So this is an example of what the code will look like and the different functions that are being performed in the code. Right here at the top are different things that I've imported to provide information for the code to run. Once we have our code and we're happy with everything, we've tested it, we know that it works. If I want to then ask someone else to view this to make sure that everything is working as it should, or if somebody is interested in using the same workflow in their particular application, but they want to make a few minor edits, we can share this code freely and quite easily. So you just click this get link button at the top. It gives you a link to the code. You just copy it and then you can email it to anyone and share it, and they can just click on the link and they'll get direct access to this code. So yeah, it makes sharing workflows quite easy. It makes sharing results quite easy. So it's a very useful feature. Just one thing to note, when you are sharing these codes to perform these different analyses, the assets that you import, so if you've added your own shapefile into your specific Earth Engine profile, you need to make that specific asset publicly available so that when you are sharing the code and someone runs that code, the code is able to access that asset. So for instance, if I got this code here that is doing the land use land cover mapping for this drone image in KZN, and I uploaded KZN as a shapefile, I need to make that shapefile accessible to everyone who will potentially use this code in order for them to just click run and for the code to work. If you don't make it accessible to other people, then when you click run, it will throw an error. But yeah, more often than not, you don't need to worry about that. Yeah, so you can get a link to share your workflow to help you share your results. Up here is the run script function, which will basically execute the code for you. I'm not sure how familiar you are with other programming environments. So within environments such as R and Python, you can run your code in blocks. So you can just highlight a section of code and click run, and it will only run that highlighted portion for you. To my knowledge, Earth Engine doesn't do that. So if I click run, it's going to run this entire code. But what you can do is, if you only want to run segments of the code, we comment things out. So if you look up here, you'll see that everything is in green. So when I execute the script, all of this is not, the script is not going to try and execute a task for this information that's captured in green. And the way that we comment things out in Earth Engine is we use this // So if I remove the // you see automatically it throws an error because it doesn't recognize this as a function. It can't execute any specific task. So the reason we include comments is it's like adding notes to your workflow, to your method. So it gives you an indication of why you're doing certain things and how to go about doing certain things. So in this instance here, I'm just capturing information to tell me which is the blue band, which is the green band, red edge, and so on, just so that when I'm generating different vegetation indices that I'm using in the land cover mapping, I make sure that I'm accessing the bands that I'm interested in. The next tab here is the reset tab. So if you want to clear anything within the map or within the code or within the inspector environment, you can do that. There's this apps function here. So, and it's another nice unique feature about Earth Engine. And I'll show you the actual app that we've developed shortly. But just to say that if you've developed this workflow and you want to share the results with someone, most of the time, the people that you are sharing the results with or demonstrating the results to, they aren't interested in the nitty-gritty of the entire workflow. All they're interested in is seeing the final result. So you can write your code in such a way where you only demonstrate the final results, and then you create an app from that. And once you've created the app, it's a similar process as sharing the workflow. You get a link to the app, you share that link with somebody, and then they can just open that link and view the results only without having to visualize any of this code. So it's just a way to present the results in a more digestible manner for people to easily comprehend what you've done. Okay, before I move on to the next window, everyone have a basic understanding of what these different tabs are providing you with?
Yes.
Okay. So the inspector tab is comment. Okay, so kindly explain again on the images. Okay, can you tell me exactly what you'd like me to explain about the images? And then I can go through it again. Okay, so I'm not sure whether you're typing your question in the chat. If you are, as soon as I see it, I'll go back to it and answer it, but I'm just going to continue for now. So has everybody worked with ArcGIS before? Or QGIS?
Yes.
Okay, so this inspector
Yes.
tab is basically providing you with a similar function as the info icon or cursor within ArcGIS or QGIS. So once you've got your image uploaded and you want further information about a specific point, you come to the inspector tab, you'll see it changes from your standard cursor into the crosshairs. You click on a point, and then it will give you the coordinate information and any other information that's available there. So if we had like 4 or 5 different raster layers loaded within our environment, it would give the value of that specific pixel at that specific point for each raster. So the inspector tab just helps you to interrogate that specific area of interest in a bit more detail. The console is used to provide you with information about your processing as you move along. As you undertake certain tasks, you can write information to the console so that you can visualize it and ensure that what you are attempting to do is actually being done. So I'll just give you an example over here. I'm going to comment out all this other information. So in this specific script here, I've defined a region of interest that I want to work with. So a shapefile or a boundary for my specific area. And within Earth Engine, you need to declare things as variables upon the first time that you want to use it. So we start off by typing in VAR to specify that it's a variable. I'm calling this variable ROI, which is region of interest. And there is a specific region of interest that I uploaded as an asset. So it's for a smallholder farm here in KZN, which I had a shapefile for. And you can see right at the top here, it's listed there. So if I go back to my assets tab and I wanted to bring in that shapefile, you can see that there's all the different assets that I've uploaded. I just go and find the asset that I'm interested in, and there's this arrow. And if you navigate over it, you see it says import into script. So I can import it into the script, give it a name, and then I'll be able to access it when I want to work with it. So I could have left the name as table or ROI, but I changed it to something that I'll be able to easily track. So from Swaimane, I changed it to ROI. I've added another region of interest that's a larger boundary, just in the event that this boundary is too small for me to capture all the information I'm interested in. I've got a secondary one. Again, that's not really necessary. The image that I want to work with. So again, I've uploaded my drone image here. I've imported it, I've called it image. And at the bottom here, I'm applying a filter function to this particular image. So in this instance, I didn't really need to do it because there's only 5 bands captured within this image. But you could be working with another image which has got hundreds of bands, or 20 bands, or 30 bands. But for your specific analysis, you're only interested in working with 5 bands. So rather than you having to download the entire image, take all of the data, and then filter out at a later stage, you can easily do that with a single line of code saying, okay, I'm only interested in working with these particular bands, exclude everything else. And then if I run the code now, it's going to print some information to me or for me in the console. So I've just executed my task. It's giving me all the information about this image that I've just imported. So at the bottom here, I've said, print this image and call it a drone image. And in the console, it's written this information for me. So now I can investigate this further. So it's showing me that it's imported a drone image from this specific folder. This drone image has 5 bands. It does the numbering from 0 to whatever the last band is. So there's 5 bands here. So it begins at 0 and it ends at 4. And there's some property information associated with it. And then the name that we specified here. So in the console, during multiple processing steps, you can print out information just to make sure you're on track and whatever you want to be done is actually being done. You can also print out graphs for you to inspect your results in detail. So you can do a lot of on-the-fly analysis within Earth Engine. That's quite nice in the sense that you get a feel almost instantaneously for whatever you're attempting to do, whether you're on the right track or not. One of the limitations is that it does have a memory limit. So if you're performing some very computationally intensive tasks and you want on-the-fly analysis, so you want to visualize, for instance, if you were doing a land use land cover classification over the entire world and you've developed this code to perform that, if you want to visualize that at the Sentinel-2 spatial resolution, which is 10 meters, that's quite computationally intensive. So that on-the-fly analysis will probably bomb out because you have a memory limit. So I think it's like about 5,000 pixels or something that you can display on the fly. While that is a limit, you can do something where you run it in batch mode, where you can export your output to your Google Cloud Drive or something like that. And that processing can take place over multiple hours over the course of a number of days, but it will run in the background. It's just when you want to visualize things on the fly that you are limited by this memory limit. So it's just something to be aware of. And then this tasks tab. So if you're running this, as I said, you're running these analyses and you know that it's quite computationally intensive, or if you want to export the output of whatever processing that you've just done, you'll write a function to say, export this output for me and save it in my Google Drive. And all of that information that you, or all of those tasks where you're performing some export function, they will appear here under this tasks tab. And then if you click on this task tab, you can see you can open it in the drive where you can actually visualize where the output is going, download the data from there, and then you can work with it on your own personal machine. So it will, thereafter, you won't be using Google's computing infrastructure, you're going to be using your own. But a lot of the heavy lifting and hard work that was required for that specific task would have been undertaken in Earth Engine. And then finally, we have the map here. So if we wanted to visualize spatially the results of the different processing that we're performing, it would pop up in this viewing window here. And there's multiple ways that we can view. And you'll see that now as we run through some of the examples. You can change the view here from this map view into a satellite view. You can zoom in and zoom out as need be. And then at the bottom here is if you need to specify like regions of interest, there's different ways that you can do it. So you can drop a marker and say, okay, identify images for me that intersect this marker. Or you can, rather than uploading a shapefile, you can draw a shapefile here over your region of interest and say limit the analysis to just this bounding box. So there's different things that you can do here at the bottom. And then we have this search tab here at the top. So if you're interested in a particular data set and you don't know how to access it, you don't know how to write the code to pull it up, you can just come here to the search tab. So can anyone suggest a data set, or would you like me to show you the entire catalog just to see what's available?
Just show us what's available.
Okay. So just move this back. So if you go here to search places and data sets, you just click within that tab, you'll see you can browse the data catalog or suggest a new data set. So I selected browse data catalog, and it's taken me to this separate web page. And in here, you can see it says home, view all data sets, browse by tags, and so on. Landsat, Modus, and Sentinel tend to be the ones that people most frequently utilize, but there's much more data available than that. So I'm just going to click on view all data sets. It's going to take some time to load. Okay, so this is all the data that is currently sitting on Earth Engine. So remember from the quick presentation, we said there's petabytes worth of data. So as you can see, this is all the data that's available to you. Majority of them are the entire image collections for Sentinel, Landsat, Modus. There's hyperspectral data. There's climate data, elevation data. So there's quite a bit of information that you can access here to perform a range of analyses. Detailed soils information for Africa, for different soils properties. And yeah, the list goes on. So now let's start actually having a look at some of the data sets and how we bring them into Earth Engine. So I'm just gonna exit the script. Okay, so can anyone suggest a data set that they've heard of? Either a climate data set, one of the remote sensing data sets.
Vegetation.
Okay, vegetation. Do you know a specific sensor or a specific indice that you're interested in? So the one that's frequently used, most people are familiar with, is NDVI. I'm assuming everyone knows what NDVI is.
Maybe we can
I don't know.
maybe we can use Landsat 8
Okay,
data set for.
so let's go first with NDVI and then we'll go with Landsat 8. So I'm just going to type in NDVI. And I see there's different options here, so I can click on more. And it gives me a list of all the data sets that are available within Earth Engine that relate to NDVI. So it could be NDVI or it could be something that's very similar to NDVI. So there's multiple NDVI data sets that are available. I would probably go with the MODIS NDVI, since that seems to be the one that's most frequently used. With MODIS, you get two sensor overpasses. So you get the Terra data set and the Aqua data set. That's basically one sensor is traversing a region of interest during the day and the others later on in the days, could be closer to the evening. It's just two different times. So I'm going to click on MODIS. So it gives us a description of what this data set is. So the NDVI is a type of vegetation index. It's just giving us an indication of multiple characteristics associated with the vegetation. So the density, the health, the vigor, and so on. So it's often used as a surrogate to describe the biophysical properties associated with a specific vegetation class. So it's multifunctional. Okay, so in here, you can see there's descriptions, there's bands, there's terms of use, and there's this small arrow right at the top. So once we selected on the data set, I'm just going to go back and repeat this whole process so everyone's familiar with how we got here. Allow it to close. Okay, so in the search bar here, we typed NDVI. We clicked on more to expand the list fully, but in this particular instance, I know which product I'm interested in. So it's this MODIS 250 meter product. It's globally available. This window here then popped up. And the small arrow at the top, if you click on that, it expands it. It opens a separate web page. And in here now you can really interrogate the data further. So you get this description as I mentioned. There's a tab with all the different bands that are available within this data set. The terms of use, it shouldn't be any major concern because it's freely available as long as you cite it. There's the citations where you can find the reference for this particular data set, and then the DOI to actually go and access that particular paper. But this is the really nice thing about Earth Engine. So even if you aren't familiar with coding, you get these snippets of code that are provided to you. So you don't need to have any coding experience to actually start working with Earth Engine. Obviously, the more frequently you engage with it and the different tasks you try to perform, the easier it will become. But just at the outset, if you are a novice and you are interested in opening this data set in Earth Engine, there's a snippet of code provided for you to do that. So I'm just going to copy this. So I can highlight it and copy it, or you can see if you navigate to this icon here, you can copy the code sample. And I'm just going to close this window and open up new Earth Engine tab. Is everyone still following along for now?
Yes. Yes, we are following.
Okay, perfect. Just check this chat whether there was a question. Okay, Landsat. We'll do Landsat after this example. So yeah, I've copied the code, just paste it into the tab, and now I'm going to run through what this code is doing. So remember I said when we first want to work, we need to declare it as a variable. So we start by typing var, the variable that we're defining, and then we calling a specific function. So this MODIS NDVI data is an image collection. So it's not an individual image at a specific moment in time. It's a collection of multiple images across the entire data set. So if I come in here, data set availability. So this is from 2000 to 2022. So 22 years worth of data that we can potentially access if we are interested in. So yeah, this EE image collection is just specifying which image collection we want to work with. See, it has a unique name here. Then we can filter this. So we obviously now don't, for this particular example, just to display the data, we don't want a full 22-year record. I can apply a filter function where I specify a particular date or date range that I want to work with. So in this example that was given with the sum is only for 2018, so from the beginning of 2018 to May. We then created a separate variable where, and remember in this image collection, when we looked at the bands, we saw that there was multiple data sets or multiple bands that were available for us to potentially use. So as I said, to improve the efficiency of our analysis, we don't want to download every bit of data that is potentially available. We only work with the data that we're interested in. So I can create a new variable now called NDVI, and then from this data set, only select the NDVI band. Thereafter, they're specifying a color palette. So when I display this data, I can visualize the different NDVI classes. I can then zoom in onto this map when I'm visualizing, and then I actually add the NDVI data set onto this map. So again, none of this code I wrote. I'm just explaining what the code is doing. But from here, you can copy this code and paste it and test it yourself. So once you've got the entire code in, you click run. And then depending on the speed of your internet connection, it's going to display the data for you. So in a matter of seconds, you've accessed a global archive. This is for a 5-month period, but it's only displaying the first image, but you've been able to access the global record of NDVI. Now, the real beauty of Earth Engine is that if you were to do this in the traditional sense and you wanted to get the 22-year time series of NDVI for Africa, you would have had to go into something like Earth Explorer, find the MODIS NDVI dataset if it was there. Otherwise, you'd have to download the raw MODIS data for the full 22-year record, do all the processing to convert the raw data into a vegetation index, clip it for Africa, do your zonal statistics on that, and then eventually compile a time series either in the CSV or in Excel. And it would probably take you forever to do that. Within Earth Engine, we can do everything that I just described within less than a minute, and then export only the data that we're interested in. So only that CSV file with the time series, we can just export that and download it directly from our Google Cloud Storage. So I'll demonstrate that just now, but the next requested data set was Landsat. So anything specific with Landsat?
Excuse me, sir.
Yes.
Maybe because, okay, we have done the NDVI index. Is it also possible to do the, if we can do also one index for water, like the normalized difference water index, is it possible?
Yeah. So as I said, there are some built-in functions within Earth Engine. So NDVI, because it's such a popular indice to generate, there's actually a function available within Earth Engine that you call up. Alternatively, you can create your own custom function. So as long as you know the equation for generating NDWI, you can easily implement that within Earth Engine. But I think NDWI data that's already been generated. So I just typed in NDWI, and this is the list of all the NDWI data that's available. So there's a whole Landsat record, there's a MODIS record. So you could just access this directly without having to do any additional processing by generating the index on your own. Alternatively, if you wanted to work with, for instance, Sentinel data, because it has a finer spatial resolution, then you'd have to actually import the raw Sentinel collection and then perform some calculations to generate the NDWI and then download that. I'll show you an example of a of an index that I calculated, just so you get familiar with how that's done. So yeah, Landsat 8. Another nice feature about Earth Engine. So if you were to work in the traditional sense where you wanted, for instance, to download this Landsat image, you would download the raw Landsat image. You still need to perform some sort of processing on that image before the data becomes in a usable format. So the data is usually archived in something called digital numbers, and then we need to pre-process it to get top of the atmosphere reflectance and radiance and do some corrections for radiometric and atmospheric distortions. So that gives us a usable data set. Now, as I said, if you're doing it the traditional sense, you would have to download the data, you would have to perform those corrections, and then you can use the newly processed data, whereas in Earth Engine, you can access data that's already been pre-processed. So you don't have to worry about that intermediate step before you work with the data. So that's another advantage. So again, we search Landsat 8. I just click at the top here. You can see the description, what Landsat 8 is providing us with, the different bands. So because Landsat 8 is a sensor capturing information in different bands, it's not an index that's been derived or a product. So there's multiple bands that are available. So we go from band 1 to band 11 here. There's a quality assurance pixel, gives you a description of what each band represents, the wavelength in which the information is being captured, the spatial resolution of the pixel for the different bands, and then from what time period the data is available. So at present, if you want to work with Landsat data, you would either access Landsat 8 or Landsat 9. They run concurrently. Each Landsat sensor provides you with information every 16 days, but if you're working with both Landsat 8, Landsat 9, then you can get information every 8 days. If you want to work with historical Landsat data, then you go from Landsat 7, 5, 4, 3, and 4. Okay, then some properties about the image. So this is all the metadata that's associated with the image if you're interested in reading that in terms of use. But back to our example where we're just calling up the data set and visualizing it. So again, I can just copy the snippet of code without having any idea of how to run code. Paste it in, click run. And there's the Landsat imagery for this particular region of interest. So we've called up the Landsat image collection. We specified a date range. We created this variable called true color. So when we looked at the number of bands that were available in this Landsat image, there were 11 bands, but for visualization purposes, we're only interested in the red, green, and blue. So we created a variable called true color 432, which is basically showing the red, green, and blue. So see, band 4 is red, band 3 is green, band 2 is blue. And these are the bands that we selected from this data set. We specified a color palette to visualize the data, and then you can zoom in on your specific area of interest and also add the layer to the map. You don't necessarily have to specify a scale for visualization purposes. Come in here. So at the bottom next to map and satellite is layers. So these are all the layers that you're adding into this map viewing window. And you can see there's this layer that we added, true color. There's a settings tab next to it. So if I click on that, so it shows that it's displaying the data across 3 bands, and the range that we specified is 0 to 4. So we specified a custom range. Alternatively, I can stretch it across the entire range of values that are present. Click apply, and then it will change the visualization characteristics. This is probably not a really nice image because of the amount of cloud covering this area. So it just a change of the date range doesn't even take me 5 seconds to do. I click run. And now instead of looking at 2017's imagery, I can look at 2016's imagery. Also, again, quite cloudy. But just with the simple change of a line of code, I've now accessed a whole nother year's worth of data. If you had to do it in the traditional sense, then yeah, you'd have to go and download a whole other year's worth of data, open it in your GIS environment, try and do some processing on it, and then work with it. So the speed of analysis here is unparalleled if you compare it to your traditional method. Okay, so before I go on to an example of where I've calculated the vegetation index based on the previous question, is there anything anyone would like me to demonstrate on another data set? Okay, so let's go into generating an index. Okay, so I will send my email address. I'll upload today's presentation and my email address is on that presentation. Let me just type it in here quickly so everyone can access it now. So I've put both of my email addresses in here. One is my personal one and one is my university one. You can contact me on either one. I tend to respond faster on my personal email address. Okay, so
Can you show the email again? Or you send the email?
sorry, I missed that. I didn't hear you clearly. Okay, since we okay, so this here now is an example of a code that's written out to perform quite a complex task, but it does it quite simply. So I'm just going to zoom into an area in South Africa, or better yet, okay, so I'm just going to import the KZN shapefile. Hopefully this demonstration example doesn't take too long. Okay, so I've imported the KZN shapefile for me to work with. I'm just going to give it a different name so that the code doesn't need to be modified in any great extent. Right, so as I mentioned previously, you can add nodes to different types of processing tasks that you're doing. So at the top here, I'm specifying which is my region of interest that I want to work with. So I imported the KZN shapefile, and then I've created this variable called region of interest just to show me where the shapefile is sitting. And then I want to add it to the map. I want to zoom in onto that particular region of interest. I then want to specify a start date and end date for my analysis. So in this particular example, I'm looking at a 4-year record from 2017 to 2021. And I'm also stating that the dates must be listed sequentially or in chronological order. For this particular task, what I wanted to do was generate another index called the Enhanced Vegetation Index. So it's very similar to NDVI, but some of the limitations that you experience with NDVI, this index manages to overcome. So I wanted to see how the two compare. I also wanted to do this at a very fine spatial resolution. So I didn't want to use the existing data sets or products that are provided by MODIS and Landsat. I wanted to take advantage of the spatial resolution of Sentinel, which is 10-meter spatial resolution. So I had to go and create this function to now enable me to to generate this data at this fine spatial resolution. So at the outset here, I'm specifying that I want to work with the Sentinel-2 image collection. I want to filter this data set only for my particular region of interest. So in the previous examples where I was showing you how to display the data, if you look carefully, you'd have seen that it's displaying it for the entire globe. Even though we're zooming in on an area just to visualize the data, if you had to zoom out, you're going to see that all the data available for the entire world is called out. That is going to become too computationally intensive for us to do. So we just limit it to the areas and the data that we're interested in. So yeah, in this instance, I'm filtering it to a specific region of interest. I'm specifying a date range that I want to work with. I've already declared that at the top. And then depending on the type or the data set that you're using, there's different ways that you can go about specifying quality control for the data. So for the Sentinel-2 data that I'm working with here, I specified that I only want the images that have 20% cloud cover or less. You can also add a cloud mask, so you don't have to specify this constraining criteria. You could just say, okay, give me all the data, but wherever there's cloudy pixels in that image, just mask them out of the analysis. Thereafter, once I've got all my constraining criteria, so what I want to limit the data set to, I can clip it just for my region of interest. So even though I'm specifying all of these things here, it's still probably going to give me an image that's larger than what I'd like to work with. I only want to work with a small region or a province within South Africa and not the entire African continent or something like that. The next step is I need to create this function to generate this index for me. So it's just a simple mathematical representation. So you can type out your equation in here and then specify what information for each variable or where each variable is within this equation. So something like NIR is the band 8 in the Sentinel image collection. Red is band 4 and so on. So I'm just giving this function all the information that it would require so that when I apply it to the image collection, it knows exactly what to do. And instead of me having to manually apply this function to every image in this image collection, there's a special feature in Earth Engine where it's called map. So if you're familiar with programming, it's probably called a for loop in some of the other programming languages, but in Earth Engine, we specifically use the word map. So we're mapping this function to the entire image collection. Then I want to create a time series plot of this vegetation index over my period of interest, and I want to visualize that. And then thereafter, what I'm interested in now to perform my own analysis is that I want to export the average value across this region of interest so that I can perform analyses out of the Earth Engine environment. So all of that is specified within this code. So just click run. It's going to go through this whole process for me. So as you can see, I said the console tab will present some of our on-the-fly information that we requested. This visualization here showing us the region of interest. So we specify that we must add the region of interest to the screen. Okay, so this is the memory limit that I mentioned. So because I'm trying to visualize everything for a fairly large region, it's not too happy about that. So this is for an entire province within South Africa. So it's probably the reason why it's unhappy with doing that. So instead of me uploading a shapefile to work with, I can always come into the map window itself. Just zoom into any area and I can draw a shapefile over my region of interest. So because we're working already within KZN, let's just stick with that. Okay, so I drew in a region of interest, and as I was drawing it, if you notice, it comes up here as geometry. So I'm just going to delete that quickly. So just look at the screen at the top here. So once I select this polygon drawing tool and draw over my region of interest, it automatically imports it here at the top. So I can give it a name that I'm familiar with. So because I've given it this specific name everywhere else in the code, I'm just going to call it that there. And I click run again. So now it should run a lot faster because it's a far smaller region to work with. It's still unhappy to generate the chart. Let us specify a shorter time period. It's fighting with me today. Okay, but anyway, so it might not have generated the chart in this example because I've exceeded the memory limit. But if you see here under tasks, there's an unsubmitted task. So if I click on run, it'll tell me the task that I tried to initiate. So what I want to do was get this time series of values with this specific period. This is the file name. I'm saving it in my cloud storage in this specific folder. So I just click run. And then it'll start executing this task. Then I can go to that folder in my cloud storage. That's taking some time to run, but let's go to another one in the meantime. Okay, so it's done. So in about a minute, it's processed all of the information within this polygon. It's calculated the average value for me. This is what we just worked with now. Download it so it's easier to visualize. Okay, and then it's printed out all of the data. So it gives you a lot of additional information that you don't really require. So you can just remove that quite easily. And now you got just the data you're interested in. So it's given us the date range and the average value for that region of interest. So this is what our time series would look like of this vegetation index for this particular region of interest. Doing some weird things with the visualization there. But yeah, so quite powerful. A whole year's worth of data, just in a matter of seconds, we are able to do all the processing on fairly large imagery and generate the time series information that we are interested in. I'm going to try working with another point here to more clearly display some of these maps, the time series for these maps. Let's see. Run here, see what it does. Okay, so that was fairly quick because this data is quite coarse resolution over a small area, but basically, so what I've done here is for a particular region of interest, I wanted daily rainfall data. So again, I specified the region of interest that I wanted to work with. I specified the time period. This is a 2-year time period. Let's make it a bit longer. Okay, so that's about 6 years worth of record of daily data. So I specified the data set that I want to work with. And then a function to calculate the average rainfall within this region of interest. So I just click run. So some information is being printed to the console. So it's telling me the collection that I'm working with. Yes.
My screen is not changing. I'm still seeing Google search. I don't have the changes. I'm not seeing the changes you are making on the.
Oh, sorry. Is that the case for everyone?
I don't know. I've put a text, but no one is responding. I don't know.
Yes.
Okay, sorry about that.
You can see this one. I think for me, I can see the changes.
Okay.
Can also see the changes.
It is
Okay.
only me. Then.
I'm not sure what the issue could be on the other end there. Yeah, I don't know how we'd resolve that. You probably try logging off and logging back in.
Yeah, let me try again logging.
Okay. So in the meantime, I'm going to continue and you can just ask any questions when you return. All right, so as I said, 6 years worth of rainfall records we called up here. You can see there's all the rainfall images that are present within this list. So we got like about 100. In fact, there's more than 100. I just asked it to print out the first 100. There's a chart displaying the data. Again, if you want to there's a time series of rainfall. So for the past 6 years, all the average rainfall in that particular region of interest. So because this was a fairly small record, we didn't have that memory exceedance issue. So we could plot the chart. And if you want, you can just download a CSV file directly. This that we've expanded. Alternatively, I wrote a task to export the data. So I can export the data as CSV and then open it up Excel or something like that and work with it thereafter.
Excuse me.
Yes.
I think Infix Hot 11 should demute the mic, otherwise it's very disturbing and we cannot hear you properly.
Okay. Yeah, so if anyone who doesn't have a question and has the mic on, please mute yourself. Okay, so did everyone understand what just happened here with the specific processing task? So basically what I want you to take away from this is that a traditional sort of data download and analysis that you would perform, for instance, if you wanted to access this rainfall data, you would have had to download 6 years worth of daily imagery. You would then have to process each one of those images manually in an environment such as ArcGIS or QGIS. That generates a lot of additional data during each one of those processing steps. And then you'd have to perform some statistical analysis on each one of those images to finally produce one column in a CSV file or in an Excel file that you would potentially use as an input, let's say, to a hydrological model. Quite a cumbersome, lengthy process, which can introduce a lot of error into each one of those steps that I just described. Whereas if you work within this particular environment, within a matter of seconds, as I said, it depends on the strength of your internet connection, you can do all of the processing that I just spoke about. So again, if I wanted to extend this, not 6 years, let's make it 10 years. I just change one line of code and rerun. This. So just rerun. And then it does all the processing again. So now it should take a little bit longer because you specified a longer time period. Yes, you can specify a different region. So that's the next thing I was going to demonstrate. So this took about 20 seconds to generate this time series. But you can see now we've got 10 years worth of record fairly quickly. Okay, so let's shorten this time series again, just so that the analysis happens fairly fast. Okay, so it's a 1 year time series, but now let's say that we wanted to work in a different region of interest. So if you had different shape files at different points that you uploaded, you could just call them up. Alternatively, we can just take this polygon that we drew to specify a region of interest, just click on it, drag it elsewhere, click run. Okay, sorry about that, click run. So see, it centralized the image viewpoint to the different region of interest, and then it's populated it rainfall for a completely different area. So you can see that the rainfall also looks different. Okay, so quite powerful tool. This is just some very basic analysis that you can do, but more often than not, it's these types of analyses that most people are interested in. Then you can get into some of the more complex sort of analyses. So before I move on to that, are there any questions? Okay, so I'm going to go back into the first code that I opened up about the drone image. So this is, as I said, I was trying to do some land use land cover mapping within a smallholder farm setting. So the reason why we use drone imagery here and not the satellite Earth observation data that's available within Earth Engine is that the spatial resolution of the satellite data sets is too coarse to capture the heterogeneity within these farms. They have plots that are less than 2 hectares in size. So majority of the time, there's multiple different farm plots captured within 1 pixel, and each one of these plots represents a different type of agricultural activity. So we wouldn't be adequately describing what is present on the ground. So we took advantage of the drone technology that we have available. And yeah, we tried to perform some land use land cover mapping, but at the same time, using all the built-in functionality that's available within Earth Engine. I'm going to run this, and then I'm going to quickly run through what the script is doing here. You're not expected to perform these sort of analyses at this moment in time, but there's a lot of good tutorial information about how to go about doing this. So this drone image here is probably about, I'd say, a gig in size, and in a matter of, I would say, less than a minute, all the processing that's required for this particular task will be done. None of it is being handled by my computational resources. This is all being done on the cloud, on the fly. So just to describe what's going on over here. So we have this drone image, which has information in these different bands. What I've asked the code to do is just to zoom in on the actual farm. So you can see there's multiple smallholder farms distributed here. So we've got maize, sugarcane, some neglected and underutilized crops. So let's switch these layers off quickly. And then these are interspersed within some fallow areas. We see there's dirt roads, there's buildings, etc., etc. So we want to be able to distinguish these croplands from all the other land use land cover classes that are present, just so that we can provide these farmers with clearer indication of which one of their farms are performing optimally. So if we're expecting a certain yield, obviously there are certain vegetation characteristics such as the health, the water use, etc., that need to be monitored, that we can link back to the yield. So we're starting off by having a detailed land use land cover map enables us to provide them with custom information for their specific plots. So this is, yeah, just to visualize the actual farm. Thereafter, when you're performing land use land cover classifications, this is a supervised approach. So what we do is we take advantage of the machine learning algorithms that are available within Earth Engine. So these enable us to establish quite complex relationships between different variables, and then use those relationships to help us do some predictive analysis. So the supervised classification is we basically tell the algorithm that in this particular location, we have something that is maize. In this particular location, we have something that is bare ground. This is a building, etc., etc. So based on the known information that we provided with, it starts developing relationships between these known land use land cover classes and different variables that we are interested in. So some of the variables that are included in this particular classification example is the different bands, the raw data that's within the drone image, as well as several indices that we can generate from these data sets. So things like NDVI, EVI, SAVI, etc., etc. So these are all just additional distinguishing characteristics that we want to add into this algorithm that we're developing to help us clearly differentiate between the different classes. The information that's printed here on the side is telling us, okay, we've imported this drone image. This is the projection that's associated with it, whether it's universal transverse Mercator, whether it's WGS84 and so on. This is the spatial resolution of the image. So this is very high resolution imagery, 7 centimeter. I didn't specifically need to work with the 7 centimeter resolution image, so I upscaled it to a 1 meter resolution. This is the training information for the algorithm. So that whole process I described by giving it information on known land use land cover classes. And then also some data that we reserve for validation. So once we've built this algorithm and we've run this model, let's test how accurate this model is. So we reserve some of the data for testing purposes. This is just a plot showing me which bands or which indices that were used in this algorithm had the biggest influence on the outcome. And these are different performance metrics to judge how well the classification performed. So you can see that overall, we got about a 91% accuracy. Yeah, there's some other performance metrics that you don't really need to worry about. Then we can display the output. It'll just take a little bit of time to load. Yeah, so it is possible to throw an error if the stat, so let's say you're trying to get the average value for a particular region of interest and you write this function to calculate the mean for that region of interest. If the first, so if you specified, say for instance, 2011, 1st of January, if there's no data for the 1st of January, it'll throw an error and it won't perform the calculation, but it will notify you that there is some error that's occurred along the way. So what you need to do then is either go and check your code to make sure that there isn't any error with the function itself, or you just change the period of interest that you're working with. Okay, so this is the output of the classification process. So what is being shown here now is we've given it some information of known land use land cover classes. We told it this is all the distinguishing characteristics associated with those known classes, use that information and perform predictive analysis over the entire image. So these white dots or these black dots are basically all the areas where we had this known information. So you can see it's scattered everywhere throughout this region of interest, and it's it's not for the entire image. So we're just using a sample of the entire image that we are working with to do the training. But when we run the predictive analysis, it runs it over the entire image. So this is quite computationally intensive. If you had to do this using a traditional approach, depending on the machine or the specs of your machine, this might take a really long time, or it might just throw an error and your machine will shut down. Yet in Earth Engine, it took me less than a minute to generate this final output, to perform all of these accuracy analyses. And the beauty of this is now that if I'm satisfied with this specific algorithm to perform predictive analysis, if I get another drone image that I want to work with. So let's say we did this land use land classification for today. If I get another drone image sometime in December, I don't have to go through this whole process again now of compiling the code. All I have to do is just import the next image and rerun the code. And in a matter of seconds, it's going to generate the output I'm interested in. So that is just an example of a more detailed application that you can perform. And then working off that existing example, if I want to share the results in a more user-friendly manner, so for people who aren't necessarily interested in all the processing that took place, they just want to visualize the final output. We can compile code to develop our own apps in Earth Engine. So this is just to test and show, to ensure that the app is doing what we want it to do. And as I said here, if you click on this apps icon, this shows you a list of all the apps that you can potentially generate. So I'm going to go to the one that we just showing now. Just take some time to load. Now it's displaying our results for us. So in this particular application, what I was trying to do is not only map land use land cover, but to identify an optimal resolution to perform the mapping. So as I said, the native drone image, or the drone image that was initially uploaded, was 7 centimeter spatial resolution, but I didn't necessarily need to work at such a fine resolution. I could have sacrificed some of the detail that I get at that higher spatial resolution and went to a slightly coarser one without sacrificing accuracy. So I was trying to test at what level will that change take place, whereby if I make the image coarser and I perform the mapping, where I start to lose some accuracy. So this app has just been developed to go and visualize those results. So without me having to now talk through the code to everybody that I share this with, I can just create this app. And so you can just look on this end at the spatial resolution. So it's quite detailed. So if I go to the image that I classified at the coarser resolution, you can see now we're starting to lose some of that spatial detail. So things that were clearly distinguishable before aren't that easy to identify now. And this app, once you create it, it will give you a link which you can easily share with anybody, provided they have an Earth Engine account. So I can, in fact, they don't even need an Earth Engine account to view apps. So I can just share the link. Let's see, let's test it in the chat. So I'm going to paste the link here. Just click on it and let me know if you can open it. So I'll just demonstrate here. So I shared the link, hit enter. Give it some time, and then it should take you to that. So someone's able to run the app now, just let me know.
Yes, it's running.
It's working. Cool.
It's working.
Awesome. So yeah, you can develop an app like this. This is while it might seem complex now because you're just getting familiar with the Earth Engine environment, this is quite a basic visualization app. You can build a lot more complex apps which actually perform statistical analyses, enable you to download products and so on. But yeah, for now, it's not my intention to overwhelm you. I just want to make you familiar with the different things that you could potentially do. Show you another app that we developed. So this example, I'll paste it here for you, so it's something that you can try. So the United Nations has developed a workflow in Earth Engine for you to map flooded areas. So if you are doing research in a particular environment that's been impacted by flooding, and you want to assess the different areas that have been impacted, but also the different types of activities that have been impacted. For instance, how much of the flooding occurred in an urban environment, how much of it impacted agriculture, and so on. You can just come into this workflow, modify it slightly for your particular region of interest, and then perform some assessments. So I'm just going to find it quickly and paste the link for you. And then, yeah, you can have a look your own time and test it out, but I'll demonstrate what we did with the app thereafter. Okay. Yeah, so this is to map the extent of flooding, as I said. So the code itself looks quite intense, and more often than not, as I said, the people that you are trying to demonstrate these results to and talk to them about it, they're not actually interested in the actual workflow that went behind producing those results. More often than not, they just want to see the final product. So instead of having to share all of this with somebody and explain to them in detail what this is doing to generate the final output, you can perform this processing, write a few additional lines of code to create an app for data visualization. And yeah, then you can do something cool like this. This is the KZN flood map that I developed based on our recent flooding events. Can't see much now, but that's because it's at quite a core spatial scale. So if we zoom in, just change the view, switch off this. Yeah, so just to note on this legend, all these areas that are in bright blue are demarcated as permanent water. So those ones we aren't interested in. We want to know where all these red areas were. We zoom in further. Durban was quite severely impacted by the flooding. Come in, and as you zoom in further, and it takes some time, and then slowly you'll start seeing these different regions pop up. So you can see some urban environments impacted by the flooding and so on. And this was done for the whole of KZN, so it's for an entire province. And I just have to navigate slightly to another region of interest, and I can zoom in again. Let me try and find a site that I know that's impacted. This is also quite close to Durban, but this area was severely impacted. I see it's 12. I don't have much more to go through, so if you can just stick around for a few more minutes, that would be great. Yes, you can see slowly all the different areas that were impacted by the flooding are now starting to show. So this is nice for visualization purposes, and then if you wanted to add some quantitative analysis to that, then it also gives you an indication of the total area that's been affected by the flood. you don't have to work at such a large spatial scale like how I've done here. You could draw a small region of interest and use that within the code, and then it would do the same thing for that particular region of interest. Then you could just change your region of interest, drag it to another location where you think there might have been flooding, and the same analysis would be performed and the same output will be generated. So again, quite handy. Okay, so that is about it from my end. One of the things that is nice to know, but probably not from the perspective of a novice user. So some of these analyses that are performed, like when I did the land use land cover mapping, I made mention of machine learning. So Earth Engine provides you with its 4 or 5 built-in machine learning algorithms, and those are the ones that are commonly used, such as classification and regression trees, support vector machine, random forest, gradient tree boosting, maxent. These are different types of classification algorithms that you can use to do different machine learning tasks. But these aren't the only ones you can use. There are some more powerful algorithms that you might potentially be interested in, which aren't available in Earth Engine. It doesn't mean because it's not available in Earth Engine, you can't use Earth Engine to assist you with all your processing. So what you could do is you could extract all the data that is required to train and test these machine learning algorithms, and then extract it from Earth Engine and go and import it into another environment that enables you to do this more comprehensive analysis. For instance, one of the things that I've done previously is to try and predict leaf area index information at a moderate spatial resolution. So I did all of the heavy lifting in Earth Engine, where I extracted all the input variables in Earth Engine. And then I formatted the data and took it into the R programming environment. And then within R, I developed a more comprehensive machine learning algorithm to do that prediction for me. So you can interface or use different platforms to do these types of analyses, but majority of the really difficult data intensive work you can still do in Earth Engine. So yeah, don't think that Earth Engine should only be limited to specific applications. If you are interested in adopting something, a different platform, there is always a way where you could potentially use Earth Engine to do a majority of the processing on your satellite Earth observation data sets or any of these other remote sensing data sets, and then work with another platform. Hopefully I didn't confuse you too much with that last bit, but yeah, if you have any questions now, please let me know. Otherwise, we can meet again tomorrow just to run through the tutorial exercise. It's fairly straightforward. But yeah, I'm happy to take any questions now.
Can you please share some of the scripts that you have shown to us?
Okay, so these scripts are for specific examples. So if I had to share them with you, they probably wouldn't be of any benefit. But when I do upload some of the additional resources for that accompany this talk today, then there are YouTube demonstrations and sample codes and things for you to work with to start learning all of this. So Earth Engine has a fairly wide community of practice, and there's quite a lot of people that are willing and able to help. So that's the nice thing about it. Like, you might find that you have a specific part of the code where you stuck with it and you just have no idea how to structure it. You can post on platforms and people will either provide you with potential solutions. More often than not, they actually correct your code for you and give you the code that you need to work with. So there's a nice website for programming problems called Stack Exchange or Stack Overflow. So a lot of the time when you're working with these types of codes and you find that you're stuck, you can then go and post on those forums and someone will almost instantaneously assist you. accessing the course material from the online website. So the course administrators are going to need to assist with this. Unfortunately, unfortunately, I don't think I'll be able to help with that now. Although if you do need anything in relation to today's talk and you're having some difficulty, you want to discuss some things in further detail, then just pop me an email and I'll respond as soon as possible. Okay, so it's 12:06 now. I'm happy to field questions until 10 past, quarter past 12. So feel free to ask. Okay, it seems like either people are shy to ask or they're satisfied with everything that's being discussed. Yeah, so if there aren't any further questions, thanks everyone for sitting and listening to me talk for the past 2 hours. I hope that I've enlightened you a bit more about the capabilities of Earth Engine, and hopefully you try to implement what you've learned today in some of your own research. And yeah, as I said, I'm happy to discuss things in further detail if you are interested in having more in-depth discussions about some of the things that we did today or anything in general relating to Earth Engine or coding. Okay, so I think we can end the session there. Cheers, everyone.
Bye.
Bye.